right. Should we get started again? I should say that one of the things we've done with this workshop was we tried our best to shorten the talks a little bit. But thank you for the speakers for letting us do that, and that allows us to have a bit more time for discussion and coffee. Our next speaker, it's a pleasure to welcome Saleh Tanveer from Ohio State University, and he'll give us a talk on Dubrovin Conjecture and Singularities of P1.
Thank you, Phil. Can you hear me all? Yeah? Okay, thank you. So this has been work a few years back with ODEs Costin and Min Huang, and concerns the singularities of P1. So as you know, a lot of you know that you're experts at it, much more than I am. P1 arises in many systems, including reduction of integrable PDEs. It's like special function for nonlinear problems. And for instance, in a problem that Dubrovin, Grava, and Klein considered, they were looking at what happens when you have initial conditions of this kind with epsilon there and the limit epsilon tending to 0. And they proposed a universal picture near blow-up time where you have gradient catastrophe, and that the structure of the solution involves P1. And in particular, their picture would not make sense unless the particular solution to P1, which is what we call Tritronquee solution, is singularity free in a sector of width 8 pi over 5. So this has been known as the Dubrovin Conjecture, and was supported by numerical evidence by Dubrovin and collaborators. So now there is a lot of work in this area, and in other problems of Painleve-I, there is a whole machinery of isomonodronic method. That's not what I'm going to talk about. This is more like classical asymptotics, except asymptotics is done rather carefully and then matched to what happens in the finite domain. So let's see. Suppose you look at the Painleve equation. I can go back here. You look at the Painleve equation, and you look for large Z asymptotics, right? So when you balance these two terms, then one possibility is for the asymptotics to have this form, and this has been known for a while. So you have a solution of this kind, and of course, suppose you require solution to have this asymptotic structure on what is an anti-Stokes line. In this case, I should also mention that there are different ways of writing P1, one with a minus sign and one with a plus sign. This is the way we did it in our paper. So in this case, the anti-Stokes line, one of the anti-Stokes line is in this direction. And if you require a solution to be behaving like this, with small o of z to the minus 5/8, then you find a unique solution with that behavior, and this has been known for a while. That's what is the Tritronquee solution is. And for large Z, it is already known from previous work that you don't have any singularity in a sector of 8 pi over 5 for large Z. So the main point of this thing is to say how big Z is, how big Z has to be before you can do that. and what happens in the finite Z domain. By the way, there are different four other Tritronquee solutions, but they're all related through transformation. So when I say the Tritronquee solution, in essence, it's unique because all other ones are related to it. Nalini Joshi and Kitaev obtained also results on the first singularity numerically at this point, and also proved that there are no poles in this direction. I'm translating their work in our present formulation of P1, so that's in their case, this result was on the negative z-axis because they use a different formulation. There are a number of results which give partial information on singularity location. I don't remember all of them, but there are quite a few here. Also, Ovidiu, Costin, and Rodica and Ovidiu, they showed that there are string of singularities that approach the anti-Stokes line at minus 3/5 pi and pi. And these singularities approach the anti-Stokes line. Therefore, the most difficult part of the proof is to control the asymptotics when you're approaching the anti-Stokes line. And this would require a multi-scale expansion, as we'll see. Now, formal arguments based on what I already mentioned shows that you have a series like this in powers of z to the 5 halves. And in fact, if you took z to the 5/4 and you did a Borel summation in the variable z to the 5/4, this expansion, even though it's divergent, sums up to an actual function through its Borel sum, which is y0. But the Borel sum itself depends on the direction you're summing, right? So this y0, when I write y0 later, need not be the analytic continuation of each other. It depends on the line you're summing up. Now, suppose you constructed that. That is the solution of the P1. The question is, what other freedom do you have? So let's say you have a general solution of y of z and subtract off from this y0, which is the Borel sum of this along the direction, say, pi/5. And then delta necessarily satisfies this equation. And then with knowing that y0 behaves like this from WKB, you know the delta has this asymptotic behavior as you go towards infinity. So therefore, when you actually require that the solution has this behavior plus O of this should have been no, it's fine. When you require yeah, that's correct. When you require this small o of z to the minus 5/8, you have essentially ruled out this homogeneous solution because they have algebraic decay like z to the minus 1/8. And I'm talking about an anti-Stokes direction because on an anti-Stokes direction, this is purely oscillatory. And requiring that this correction is O of z to the minus 8 means that C plus and C minus are both 0 on an anti-Stokes line. So it's suppressed. So therefore, you have a uniqueness argument that you have a unique solution, which is the Tritronquee solution. This is all known things, but not everyone here knows about these things, so I might better review some of it. Now, when you go to past a Stokes line, which in this case is at minus pi/5, when you go below that, then you collect contribution, this is the Stokes phenomena, then you have these exponentially small terms that are born, and S0 is Stokes constant. And we notice that if we approach this anti-Stokes line, which is minus 3 pi over 5, then it would not be, even though this is initially exponentially small, near minus pi over 5, when you go towards this point, this direction, I cannot say yt behaves like y0 anymore, because this guy becomes, when this thing is oscillatory, I cannot ignore z to the minus 1/8 contribution. So let's try to straighten variables. So this is due to Boutreau, but in general, for generic systems of ODEs, Costin has a normal form that he shows that generic systems of equation can be put in a normal form, and this is a normal form transformation. So in other words, instead of y of z, you consider h of x, and then P1 becomes this form, and notice the z to the 5/4, this transformation and this thing. What it does is what used to be the anti-Stokes line at pi over 5 argument now is mapped onto the positive imaginary axis, and the sector and the anti-Stokes line where things become oscillatory becomes the negative imaginary axis. So in this form, the solutions all have, the principal solutions are all in powers of 1 over x, and when an exponential is born is e to the power minus x when I cross the argument of x equal to 0 direction. So in general, the solution has the following behavior. You have a uniform expansion where you have a principal series, and this is H0 is denoting the principal series, or perhaps it's Borel sum, and then you have an expansion in exponential and series in 1 over x. So this is what is called a trans series in the language of Ecole. And the trans series has this exponential term, prefactor c here. Now, Costin and Costin, they actually were able to show that when c becomes order 1, that you can resum this and end up with a function of c, and by which they were able to find that you have singularities approaching the anti-Stokes line, which in this case is near minus pi over 2. So exponentially small terms resummed gives rise to singularities. Now each of these H0, H1, H2, these have these principal series in powers of 1 over x. In the case of H0, it starts from x to the power minus 4th. So this is a known thing. All right. So we have a lot of information. The result that I'm going to talk about is this theorem that we proved about 8 years back. And this is so-called Dubrovin conjecture, that in the domain D, which will show in a second, perhaps I should show now, this is the domain D in the z plane. It consists of this sector of width 8 pi over 5 and a circle around the origin, which in our case is of radius 37 over 20. So in that domain, the theorem says that you don't have any singularity. Okay? And a corollary of that is in the open sector, you don't have any singularity either. So here notice that we allow argument of z to be minus 3 pi over 5 and pi, which are the boundaries of the sector. Now, another observation about why we are able to get get all the way to the boundary is because you look at the expression for C, you have a negative powers of x here. If instead of x to the minus half, if I had x to the plus half, then for large x, you'd have a singularity on the other side of the sector, so you wouldn't have a Dubrovin conjecture, obviously. However, because of the negative power here, C stays small even when e to the power minus x is purely oscillatory, right? And that's why it's, this works at least for large x. Now, what is the strategy of the proof? We actually use reflection symmetry, and there is reflection symmetry about this line. And this line, and let me extend this line, argument of z equal to pi over 5 this way. And there is a Schwartz symmetry about this line, which allows us to just look at the domain on this side. So we call this domain D1, right? The domain is shown by hatched line, all right? So this part, this half, including this half of the circle, so that's the domain D1. So we reduce the analysis to D1, and the image of the transformation under D1 becomes the right half plane. Image under x being z to the 5/4 times some phase factor, right? And so now let's define the operator n to be this guy, right? So the basic idea is to come up with an approximate solution, which you call the quasi-solution. And in this case, each of the sectors would need a different representation. We are not worried about sectors having piecewise different formulas, because we know that if we have an asymptotic expression in a particular sector, the full asymptotics in a particular sector, including any Stokes multiplier, that there can be only one solution for the problem. So if we show each of the sectors you don't have any singularities, then that's good enough. So what we do is we come up with a quasi-solution in each of these sectors, and then this is when you are far away, and you can use the asymptotics at infinity. Then you come up to a location which is you are able to come up with a location about 1.7 in the z domain, and then you have information on y0 and y0 prime. These are the approximate solution at that point, based on y0 and y0 prime at that point, and a rigorous error bound on the difference between yt and y0 in the function as well as its first derivative at that point, then you therefore take a polynomial on this segment in order to get to the origin, and then you use your rigorous bound on the function and its derivative at the origin, and thereby determine what is the worst possible case by way of estimating the Taylor series, what is the radius of convergence of that series. So, what is the role of this quasi-solution? The role is the following. Once you get an approximate expression, then your fully nonlinear problem becomes a weakly nonlinear problem for the difference of the actual solution and E. And so therefore, this is the linearized part. When you linearize about y0, n of y0 is what we call the residual or remainder. You plug in the quasi-solution into your differential equation. That, by definition, is n of y. And n1y is basically the difference between the linearized approximation and whatever you have, and this is, of course, order E square. right? So that scales quadratically. Now, in this case, you have ODEs, and therefore you use the conditions at infinity, and you define your L inverse using variation of parameters, okay, in terms of some kernel. You end up getting this so-called weakly nonlinear equation because n of y naught is small by choice of y naught, and L inverse is bounded, and therefore you get this thing to be small, and this thing is also, because it scales quadratically, you can use Banach contraction theorem on this equation to show that in some specific small ball, you have a solution. And that gives you the error bound on E. And essentially, it becomes a problem of choice of the space, and also becomes a question of what exactly those numbers are which bound these things. Because you also have to know what restrictions you have. Now let's look at the far field first. Okay? Far field is what we start off with. We have knowledge far away, and then we get to closer, and then we do other things. In the far field, let's remember I have a domain in the z plane. I also have its image under z to the 5/4 times a phase factor, that x of z. Under that transformation, I know its image, and I'm going to show the image. Now, I have these three different cases, and the images of that in the x-plane is actually given here. So you have, as I mentioned before, the half D1 domain gets mapped to the right half plane, and so we are not now looking at what happens far, far, far away. So what we do is we look at the image. So we have this sector, and then this one we actually manipulated, made this straight, so that when you use variation of parameter formula and we have oscillatory functions, we can choose a point x here and integrate vertically. Now this is the part where the representation for the quasi-solution has to be most complicated, because you have a two-scale expansion. In these cases, for our purpose, which is basically to show there is no singularity, the choice of the quasi-solution is very simple. It's essentially two-term asymptotic expansion in X. Later on, with a student of mine, when we actually showed that Joshi and Kitaev numerical result on first singularity, we actually justified that mathematically. In that case, we need a far more accurate quasi-solution. Right? But in this case, it's enough to do this and that. And then you, over here, in this sector next to this anti-Stokes line, you have a much more complicated expression. No, you not only have this, you have this function h0, and h0 has this two-scale expansion. This is a truncation of what we call the trans series. How many terms do you include? Well, if you include more terms, you will get more accurate representation, but then, of course, you have to be careful. More terms you put in, more harder work you do. But so this is essentially what we found was good enough for our purpose. All right, so remember, we have to have things under control over here where x is sufficiently large. And c, remember, is the exponent term, e to the power minus x times x to the minus half. Yes?
Did I miss anything? You were talking about applying the fixed point theorem
Mm-hmm.
in a restricted domain,
Mm-hmm.
and you map those domains to these
Mm-hmm.
ones here.
Mm-hmm.
And you're handling each subpart
Mm-hmm.
of the domain
Mm-hmm.
separately.
Mm-hmm.
My question is, if you look at the subpart, say one of these
Yes.
triangle-shaped
Mm-hmm.
regions,
Mm-hmm.
what makes you believe that this is going to lead to a tree truncate solution?
It does.
Rather than say truncate.
that's because I'm going back to Ovidio's 95 paper, where basically if you have the principal series and you give the constant c, then you have a unique solution. And in this case, the Stokes constant is square root of 6 over 5 pi, which you know very well. And you have a unique solution in this case.
How does the fixed point theorem give you that?
Oh, can I go a little bit further? Yeah, okay. You'll see that when okay. So I will explain a bit more detail what is going on in omega 3, and I think you'll see the answer. Okay, so you have H0, which is over here, and then as I mentioned before, you start off at infinity, and over here in the finite domain, you use a polynomial representation for the quasi-solution, a polynomial of order 7, where S is t minus t naught. And so that's the choice of quasi-solution, and those are the domains farther out. Okay. Now, in each of the region, omega 1 and omega 2, those are the easy regions, because you basically have not much going on. You have this series, you truncate it, you choose your, over here, you choose your contour from I infinity to the point in question, a vertical contour. When you do the inversion, use the variation of parameter. And you can do that over here as well. Over here, you choose the vertical contours coming from minus I infinity along this, so that you can access any point in this sector. Now, okay. So these regions 1 and 2, these are relatively simple. And let's come to region 3, which is the more complicated sector. As I mentioned, this is what we use is a truncation of this trans series. And this truncation, these coefficients are not unknown. Everything is known about them. And the constant S is square root of 6, there's an I think, square root of 6 over 5 pi. So these are well known. And so then after we do the analysis far away, we then go back to the original anti-Stokes line along a ray, and then we move on up to 1.7, where we have and show that the error bounds are of this kind. Then we use a polynomial by projecting the Taylor series of y naught at the point this. We take the Taylor series at the point 1.7 e to the I pi over 5 based on y naught. You can work out the Taylor series, but that Taylor series is not the most efficient way of going about when you're trying to figure out what happens on a line. We project that to a Chebyshev polynomial, and this t naught being 1.7 here. And then that gives you a more efficient representation of the quasi-solution. And using P of t and the error bars on yt and yt prime to within 10 to the negative 2 accuracy, straightforward estimates of the Taylor coefficient at z equal to 0 shows that the solutions with initial conditions within 10 to the negative 2 of the estimated yt prime has a radius of analyticity of at least 1.85. And combining all these results, you have the Dubrovin conjecture. All right? So that's the end of the story. Now, there are a few points to make. As noted, the analysis of the integral equation uses standard contractive mapping arguments. What makes this approach possible is the high accuracy of the two-scale expansion. And in some ways, it has much wider generality because it's not relying on the Riemann-Hilbert represent formulation of P1. The probably, other than the choice of the quasi-solution, the most non-elementary part is to determine the error bounds in the region omega 3 next to the Stokes sector. All right? So let me just display how this goes. So remember, our quasi-solution, now we're using the x variable, right? H is the unknown function. So what we do is we have this is the error term. So we scale x to the power minus half and reformulate an equation for g. H naught, the quasi-solution is this truncation of the thing, and I remind you again, c is just e to the power minus x times 1 over square root of x times the Stokes constant. So this is, these are exponentials, and these exponentials near the negative imaginary axis become not so small. You can't count on the exponential, but you can still count on the fact that you have x to the power minus half, which is small. All right. So you get this equation for g, and so now comes the question of which is Nalini's point. How do we know that we have the right solution in trying to solve this? So so let's look at this problem. So for r of x is what we call the remainder term, and we have this nonlinear problem. And when you look at the remainder term, you look at it carefully. It has x. It starts with x to the minus 5 halves, and you work out all the terms. You're not ignoring anything like this. And these are polynomials, not too many terms. Polynomials in the variable 1 over zeta. Zeta is whatever this argument is. So these are polynomials in e to the power minus x. And so in some sense, this is small enough, and you can estimate the errors on this quite easily, because x is bigger than some number, and e to the power minus x is, after all, always less than or equal to 1. All right. Now, in order to invert this operator, you have to know how to solve this equation, or at least solve it in a way, or at least find a solution to a neighboring problem. So this is the problem. Now you do formal asymptotic reasoning, and you end up getting this kind of behavior of at least one solution. But of course, we are not doing formal, we're doing proofs. So you have to come up with an equation where this thing is an exact solution. Right? That's not too hard to do. You just plug it into this equation, and whatever you have, you divide that by u, and you find that y1 that we came up with satisfies this equation, where q of x times y1 is this guy. And remember, qj involves inverse power, is a polynomial in e to the power minus x. Maybe we should have called it e to the minus x here, but it's polynomial in 1 over zeta. And it starts with power 5 and bigger. So when I'm looking in a domain where x is sufficiently large, this is certainly a small quantity. All right? So you got access to one solution. To get access to another solution, because it has to solve the same equation, right? So what we do is we just basically use the fact that another solution is y1 times an unknown function, and you end up getting this kind of representation for the other function. And then you have to work hard to figure out, it's a good idea to take part of this z, and there's a log term, part of this z2, part of this out explicitly, so that you e to the 2x, and you have e to the minus x here, you have e to the x and e to the minus x. And if I'm going vertically, the exponentials are oscillatory, right? Okay, so to answer your question, when I go from here, so when I go from this equation 4, that's my starting point, right? I need to write it in the integral form, and I have to ensure that I'm accessing the solution with the right behavior. All right. So g, remember, h0 takes into account this asymptotic behavior for large x. So you come back to G, and you choose this weighted norm. You look at functions which are analytic in the sector omega 3, continuous up to the boundary, and you put this weight. This weight is to ensure that the G that you chose, which is, remember, it's this guy. You have H0. I worked hard enough to take into account all the correction to x square, right? So therefore, I have to make sure that this thing is small enough, and this x to the 5/2 ensures exactly that. So you end up inverting this. This is the variation of parameter formula. So and G naught is the expression that comes out because you have a remainder term. When you apply this kernel to the remainder term, that's the inhomogeneous term, you get this equation. Now we'll show that this has the right property. It takes object in the space that we were talking about and maps it back to the same space. So the question is, can I add solutions to the homogeneous equation, C1 y1 plus C2 y2? If you look at the asymptotics of this, you find that y1 and y2 are not allowed because they do not decay like x to the, they decay slower than x to the minus 5/2. Okay? So therefore, so therefore, you end up with this thing, and the rest of it is very careful and laborious work. We had to take into consideration that we didn't want to lose anything, because after all, you have to find a real value, a number. It's not enough to say for sufficiently large rho, this is what's going on. We have rho is 1.7. We have to give numbers. What is the error, all right? And that's how we worked out that the numbers we got are contractive, and you have a solution in that space, G equal to n of G. You have a Banach contraction theorem. So we proved, in particular for that sector, we proved the result that if rho, which is the size in the x-plane, the size of the circle, there exists a unique solution to G to 23, which is the previous equation, in a ball of size 4 in the class of analytic functions in the domain omega 3, which are continuous up to the boundary. And through change of variable of G, this corresponds to the Tritronquee solution. There have been quite a few results since our work. My student Ali Adali and myself, we confirmed rigorously the work of Nalini and Kitaev, and Min Huang, one of our collaborators, used similar methods to prove the Hastings-MacLeod solution is pole-free in this sector. Then Ovidiu and Rudika and Min Huang, they used the adiabatic hodograph method, which is quite powerful to completely determine the singularity structure for large x asymptotically. And then more recent result by Ovidiu and Gerald Dunn, they developed powerful methods by which you can get this kind of pictures. You can get the 35 nearest singularity based on 50 exact coefficient at infinity. So you can rebuild all the singularity structure. So these are quite impressive piece of work, but my contribution ends over there. Thank you. Yes.
Thank you. I have more questions, but possibly I'll pursue them with you later. But I do want to make one comment right now, which is at several points you said that my work with Kitaev was primarily numerical.
No.
Or that was the implication.
No.
But in fact, it was completely rigorous, as you know, and there were, so those estimates we gave in the tables, the many tables in that paper, were based on the analytic proof of the approximations to the Tritronquee solution over a very long interval.
I thought you put it as a conjecture, that number, 2.3 minus 2.38 something.
Well, that was obtained by reformulating the equation in a different way.
Okay,
in
I stand corrected if indeed that's the case, yeah. All right, go ahead.
Well, that was my main comment. But can I just get you to go back a couple of slides? I think it was the integral, just there. You have, this is the integral equation at the bottom of the slide that you're solving.
Should I go back? Yeah.
No, that's fine.
Okay.
So you're integrating over a very long interval along this particular ray.
Correct.
Yeah? And you have kernels in this integral, which are given by V, for example, and V0 has a singularity at 0. I guess what you're saying is...
No. Remember, our domain omega 3 is the large is in the large X domain. Okay?
But you did talk about the ball of size 4.
We first handle everything for large X. Then we take a ray along the original anti-Stokes line, which is pi over 5. Then we come towards the origin. Based on that, we come up to 1.7, and then we use a polynomial quasi-solution there, and use a quasi-solution and a quasi-solution for the Green's function, and we integrate that, and we come up with the error bound for y and y prime at the origin based on the quasi-solution. What is the difference between yt0 minus y00, which is our quasi-solution, and yt prime of 0 minus y0 prime of 0? We come up with the error bound, and that error bound is not too impressive, 10 to the negative 2. That's all we needed. Then, based on the fact that you do a Taylor expansion at the origin, with those two numbers uncertain by this amount, we are able to estimate the radius of convergence to be at least 1.85, 37 over 20, all right? So therefore, that completes the picture, because coming from far away, remember, we came up to a smaller radius than that, and then, but that was only in each of the sectors, and then having this analyticity on a size of now in the analyticity, of course, when you come to the origin, you don't use the x variable, because you go back to the z variable, and then the z variable, you actually do the Taylor expansion at the origin, and then, so together, when you put everything together, it's singularity free.
Hello, it's not a question, it's a comment. And would I be allowed to draw something on the yeah. So by the way, thank you for a very nice talk. So I would like to maybe, so the talk was about the sector, like of the size pi over 5, were pole free in the complex plane. But
the complement of that, yeah.
Complement. But the poles were sitting right here, forming some sort of a pattern. That was shown.
That's the work of. I'm not involved in that.
Yes.
Yeah. No.
What I would like to say that you can actually, in physical world, you can see those poles. If you take a solution of the focusing on linear Schrödinger equation. So this is xt plane. And you take some Gaussian type of profile, perhaps H, and allow it to evolve up here in the semi-classical, and you consider equation in the small dispersion limit. Then what you figure out that there is so this is a point where the gradient catastrophe happens, and then there is one-to-one correspondence, almost near linear correspondence between this Painleve complex plane and real xt plane, so that this structure of poles will be mapped into some structure over here, and you will see some spikes of the otherwise smooth solution, right? That represents locally scaled peregrine breezers. So that's a result of my work with Martka Bertola of 2013 or 12. So you can actually see these poles of Painleve in the physical, in the water wave experiment or fiber optics or something. That's all. Thank you.
Thank you.
Great. Let's thank Saleh for an excellent talk.
Thank you. Do we have a coffee break or no? Oh, another talk. Thank you. Oh, I'm stealing something. Here.
So that should be easy, right?
Just put in your pocket and this one on your shirt.
Okay, great. Thank you very much. Cool.
I promised I wouldn't touch it. Can't find it around, so I'm going to have to touch it.
Somehow it disappeared.
Yeah, Mr. IT has disappeared for a second.
That's the previous doc. I don't know. These are not my formula. I think I saw this gentleman, right? On this is it.
Chris, do you know where Nathan is?
We just seen. I just saw him in the corridor a minute ago. So what has happened is that I have seen
I'm
the
not sure. He's set up some full screen mode that I can't exit. So.
There is some secret password or something, right? Maybe. If anything, I have my laptop as a backup, right? So we've done something badly wrong, as it's trying to. So what's that?
Okay, so which people want?
Somehow it kept displaying the previous talk, but no chance to switch to the next one.
Somebody's shut them down.
But if I have everything with me, of course, including the oh, that's the one. But of course, it's now not anymore projecting, right?
Don't worry, trying to do it all at once. Do I need to put the microphone on?
Looks like how exactly international intercontinental rocket launches work, right? You need to do some
And that is
very
not
sophisticated. Oh, it's already showing. So I should watch my language from now on, right?
There we go.
Whatever I say.
Thank you very much.
Right.
All right, so our fourth and last speaker for the day is Valery Shmishleyev,
Well done.
who will give a talk on 2 examples of exponentially small effects in asymptotics from diffraction and homogenization.
Thank you. Thanks, Phil and Chris. It's honor to be here. A lot of nostalgic memories for Isaac Newton Institute, and to participate in this workshop on asymptotics beyond all orders, right? So I had to scratch my head thinking what if anything I could offer on the topic, and this explains a bit of eclectic talk. So I think I detected possibly 1, maybe 2 topics where I was involved, into which I was involved, and which may hit the business of exponential asymptotics. And it's one kind of bigger. It's kind of roughly the proportion of talks. I will mostly talk about this big problem, which comes from diffraction, and this is those who have worked in diffraction or high-frequency scattering, which is more or less the same, will know that this is one of notorious problems which resisted various attempts to crack it from all possible directions. People tried this and that. They tried everything, including, I think, exponential asymptotics. Then I realized maybe, whether knowing it or not, I was one of those who started my research career a long time ago. It's actually, when I was a PhD student, it was part of my nearly failed PhD, right? For the reason that that time my supervisor, Vasily Babbage, gave me this product. Tried out of fun. I tried this and that. Nothing worked. Didn't much help to my self-esteem. But as a little consolation, how many years? 36 years later, the fact that it is still largely an open problem, right? Comes as a little consolation, and that this is what did I say? Yeah, one philosophical point that this is arguably as important and canonical PDE as the area ODE is, right? Everyone knows that area function is kind of simple but very important, canonical, fundamental for connecting 2 worlds, oscillatory and exponential decay, and light and shadow, right? And on the same token, one could argue that this is, in a sense, next in the hierarchy. This is a PDE rather than an ODE, and it connects not oscillations to decays, but asymptotically model and asymptotically scattered patterns. And or you can say the same thing in different language. If in more mathematical or spectral theory, asymptotically discrete spectrum to asymptotically spectral behavior to asymptotically continuous spectrum behavior, and transition between the 2, right? It is known how to do transition for area, right? If you're an undergraduate student and you have learned basic operations with the ODEs, you need to make a step up, right? To learn a stationary phase method or steepest descent, and to connect the 2 asymptotic regimes, right? If you go to postgraduate study, then you have learned, it depends on your university, I suppose, master level, you know, separation of variables, you know, PDEs, and it similarly doesn't work, but there is no, so far, substitute to this kind of steepest descent method. Maybe exponential asymptotics could not be, who knows? The question remains, and this is, you see, that's kind of my first publication ever, and this is my last publication so far, right? Hopefully not ever, couldn't be sure. Here is the gap, right? Did some easier problems in between. This remains open, but that was the occasion, in fact, with yes, with my colleague Ilya Kamotsky, in a special issue in honor of Vasily Babbage on occasion of his 90th birthday, right? We felt obliged to just review this notorious problem and then make a little further step forward. And then on this, another possible fit to the topic of the workshop, I'll briefly mention in the very end, is in homogenization when it's actually brother, right? You see a different first letter, Vladimir Kamotsky and Ilya Kamotsky. So Ilya is my current colleague, now full professor in UCL. Vladimir is now somewhere in financial industry, used to be a postdoc with me some years ago. And we did out of final calculation when this, in homogenization you can do optimal truncation and have some exponentially accurate error bounds. Right, so here is turning to this first big notorious problem. So it started actually from late 70s, right? So it's good translation, 76, first paper in Russian, so 46 years by now, right? And here is in my first publication in red, which is, I think, directly or indirectly, as I will try convincing you, it has some exponential asymptotic ideas hidden behind it. But then there were some other attempts from, including myself, the second publication from different non-exponential directions, and one more, and a lot of other authors here. More mathematical, some are more engineering type, and then there are more recent activity, some kind of incomplete list of references, some resurgence of interest. So resurgence is another keyword, right? In exponential asymptotics, I understand. Resurgence of interest in recent years, and including a couple of papers with John Ockenden and Dave Hewitt a couple years ago, and this paper with Ilya Kamotsky in the special issue in honor of Vasily Babbage. So it's available in public domain for those interested. Now, so it is a whispering gallery of waves, diffraction by inflection. What is the whispering gallery? This is the first time I learned that time in Russia, then Soviet Union many years ago, that somewhere in a faraway London, now I'm honored to be working in London, who knew by then, there is a St. Paul Cathedral, and there is this whispering gallery, right, in the St. Paul Cathedral, and then if this is the whispering gallery effect, right? Everyone whoever travels to London, next occasion, go to St. Paul and do this experiment with your friend, right? If one guy whispers right along the wall, and the talker and the receiver, yeah.
We have that in the moment.
Right. Oh, okay. Have you tried? Yeah. Does it work? Right. I should try do experiment with two theoretical guys. I should try and do experiment after all. so anyway, this is an intuitive idea, right? That if you are here and whisper, and then the kind of the wave, acoustic wave in this case, right, wants to travel along the ray straight line, but then those rays which make a small angle with the boundary, they reflect the fact that the boundary is curved is crucial, right, important. That's why you need to curved wall. And then there is some enhancement of signal there, right? There is a kind of, or so if you start translating it into more mathematical language, bit by bit, then you should have some solutions which are asymptotically concentrated in a boundary layer, right? Near the boundary, right? So that's all pretty well understood from all possible directions, and as long as you have a curved boundary, concave, right? Let's call it, if you look from the direction of the wave field.